Welcome back, everybody. We were almost done with our MRAM lecture, except for a few slides. So we'll quickly get that done and move on to a new memory technology today. So here is what we discussed in the last class. We ended with the spin orbit torque MRAM. We discussed how we use a completely different physical phenomena to switch a magnetic tunnel junction as opposed to STT, right? And we quickly discussed the difference in the MTJ structure. In addition to free layer, pin layer, and the oxide layer, you have an extra heavy metal layer, which helps with the spin orbit torque generation. And a portion of the SOT MRAM looks like an STT MRAM, especially for the read side, but you have an extra transistor that is used to control the write operation. Now, I don't remember whether I highlighted this enough or not, but you are getting an extra benefit. In addition to getting to a new physical phenomena that requires lower energy to switch, the MTJ, you're also getting separate read-write path. Read path, write path, okay? So now I asked you whether or not you'd like to have a separate read-write path. The controversy was yes, but if it comes with a cost of increased area, do we still like it? And the answer should be a little bit political. Depends on the application. For certain application, we don't care about the area. We care about having the utmost read performance and write performance. But some other applications like portable and wearable devices, we do care about both. So then maybe not. But people are exploring technologies which will provide you with separate read-write path without the area penalty. That would be the crown jewel. Okay. Now we also looked at this 3D structure compared to STT-MRAM. It's a bit more complicated because you need two transistors. So there are two word lines, one used for read, one used for write. And apart from that, everything else is very similar. Basically, you are not missing out anything by going for this fancy MTJ structure because you're limited by the transistor area, as you can clearly see from this 3D view. I can zoom in a little bit. Okay. So apparently, yes, the MTJ was tiny. Now you need more, stuff. You need a heavy metal layer. But notice where this layer is coming. It's on the upper layer. It's at the back end of the line, as I used in the last class, right? As long as it is BEOL, people are more forgiving. So it's not a big deal for us to design this device and make this device in industry setting. The only challenge, the only practicality challenge is the increased area because of additional transistor. Now, we will address that a little bit more using layout implications. And we briefly discussed the layout of an STT-MRAM structure. I hope you remember. So this is the STT-MRAM layout. And here is the legend, by the way. You can just double check at home and make sure you understand each and every layer of this. But for the sake of time, I'm going to quickly go over it. If you look at this 1T1R structure, STT-MRAM, this entire thing is your transistor, and you have a tiny magnetic tunnel junction sitting in there. Okay, we already noticed this structure in the previous part of the lecture. But in certain design, people use two transistors instead of one. Oftentimes, they're not even mentioned as two different transistors. They're represented as two fingers of a transistor. What do I mean by that? So imagine if you have two transistors that are parallel to each other. Let me show you. So the drains are connected, the source terminals are connected, and also the gate terminals are connected. That means you essentially have two transistors instead of one. Making sense? But so when they turn on, both of them will be on together because they share all terminals. What it allows you to do is independently tune the properties of this transistor, or we mention them as finger one and finger two. So maybe you can modulate this finger transistor and not the other one, and so on, because they can have different body contact. Okay. And quite often, it's also possible in certain design to desensitize the gate terminal from each other. So meaning you can have independent gate control if you want to. So I'm going to pitch an idea here. You might be wondering, why would people want to do that? Here is why. Remember read-write conflict? You try to improve the read stability by reducing the read current, but during write operation, you have to provide more current anyways. So the same transistor cannot be designed to provide a really high current and really low current at the same time. It's challenging to do so. So how about during read operation, we just turn on one of the transistors and you just deal with this path, and the other transistor's gate could be turned off. Okay. And during write, you basically turn on both of them. That's a possibility. How about, yeah, that means you need two different gate contacts. And as you see here, this is a gate word line, this is a gate, another word line. Well, you can always connect these two gate terminals together and make them one. That way, you could just drive them simultaneously. Or you could keep them separate and control them individually. Or here is another interesting excuse me, feasibility. Maybe you can tune the body terminal of these two transistors independently and make one of them with high threshold voltage, really high threshold voltage, okay? The other one could be low threshold voltage. So when you apply a certain word line, this one turns on, the other one doesn't, despite their gates being shared. Making sense? So they have the same gate like this. But in one of the sections, you have a higher threshold voltage versus the other. Who controls the threshold voltage? There are many parameters that controls the threshold voltage. Body biasing is one such parameter. And you can body bias one of the transistors and not the other. And doing so, you could also modulate independently. Okay, so these are all possibilities for which people might want to go for two transistors instead of one. Yes. That's a great question. So it's not off limit to play with the width. We can always, the question is, instead of having two parallel transistors, why can't we just double the width of one transistor, right? I mean, that would do just fine in terms of giving you the higher current. But remember, that will still be one transistor. So when you double the width, the read current also doubles, which you don't want, because that will reduce your read stability. But when you have independent transistors, maybe you can play this trick if that is allowed. So think of it this way. If your customer, when you're a foundry, you offer these solutions that, hey, we can make STT-MRAM with this technology or that technology. Now, if you're selling to a technology, to a customer who only cares about the minimum area, sure, take this one and don't worry about this fancy technique. But you're selling to a customer who absolutely cares about both read and write performance. Okay, sure, go ahead. Take this and then we'll custom make these gates for you, as long as you don't care about the area. And just to put you in touch with actual application, imagine automotive sectors. Okay, automotive sectors don't care about area, they care about absolute reliability. Things cannot fail. But sectors like, for example, your smartwatch, or these are tiny, so area is everything, and you are limited by 2D area if you think about it, not 3D, 2D area. So then you don't go for these fancy techniques. Okay, does that make sense? So by increasing area, sorry, by doubling the width, you're not gaining anything that you are not getting out of this one. So basically, if you double the width, it will be the same size as this one, practically. Yeah. But now you have the option to offer certain customers, hey, if you want, we can custom make this portion of the cell for you to give you independent gate control. Do you want that? No? Okay, sure. We'll just connect it. Fine. Make sense? All right. So keeping that in mind, here is how it looks like from a cross-sectional point of view. This MTJ, we have seen this many times by now. The MTJ is at a top upper layer, here as well, MTJ is at an upper layer. Okay, now, you guys all with me so far? Okay, all right. Okay, so let's take a look at this one, this option, which is an SOT-MRAM, spin orbit torque MRAM. Here, why did I decide to bring up this design? Because it's not unusual for STT-MRAM to also have two transistors. But SOT-MRAM will definitely need two transistors. There is no getting away from it. Okay, so it's like a mandatory feature of SOT-MRAM. This is your heavy metal. This is the MTJ connected to the heavy metal, and you have read transistor and write transistor. Now, if you compare these two designs in terms of layout perspective, basically, excuse me, they look, I mean, just take a look at these two, this one and the other one. Just have a moment to take a look at both. Don't they look similar? Practically, it is what, and if you look at the 2D cross section, just take a look at these two figures. They're same, because all the transistors are made in the same layer. You just connect differently, that's all. And basically, this gives you an option. Notice here we mentioned RWL, read word line, write word line. So we are definitely making them independent. But here we mentioned word line because you could make them like just connected, or you could make them independent. It's up to you. There is an option. Making sense? So if you are just going after separate read write path, okay, I think I skipped that part as well. I don't know if you caught that, but in addition to having both transistors work together during write and just one working during read, it's also proposed that make one of them work during read and the other one during write, meaning this could be a read transistor, this could be a write transistor. And this could be really strong in terms of, it could have lower VT and this could have higher VT. You could independently design them. So during read, you use this path, during write, you use this path. So you can have separate read-write path in an STT-MRAM structure as well. Okay, if you don't appreciate, oh, okay, so why would we go for this degree of, area? Just take a look at this structure. That was STT as well. Remember, STT-based read, STT-based write. But look at that structure. How complicated was it? It requires less area, but it is so complicated to fabricate. So people just proposed, instead of going with this complicated structure, let's just add an extra transistor and let's see how much area increase you get and can we live with it. So that was the motivation. Now for SOT, you have the same structure except for two changes. Number one, your read and write will definitely be separate. And number two is you have an extra layer, which is this one. This is the heavy metal layer. As you can imagine, this is the heavy metal layer. Okay, I guess he's still with me. And by the way, this legend will tell you SOT material is basically the heavy metal, spin orbit torque material, and typically heavy metals are spin orbit torque materials. Okay, and from a cross-sectional point of view, in addition to the MTJ, you have an extra layer of heavy metal. That's all. Interestingly, we will discuss some other memories coming up, including phase change memory, resistive RAM or memristive memory, ferroelectric memory. All of these memories have an extra component in this layer, meaning back end of the line. Ferroelectrics is different. There is a difference in ferroelectric memory, but keeping that aside, most other memories will have this feature. You can make all these fancy structures and devices at the back end of the line layer. So sure, this versus this, there is a very different physics involved in the write operation. But essentially, for the manufacturing point of view, they don't add any extra challenge for you. Okay, one extra layer of metal, you don't care. I guess still with me? Okay. All right, let's take a look at some other information here. I know it's a very busy slide, but I wanted to keep them in one slide because they are all from the same source. Excuse me. So in case you want to look it up, and I do recommend, please try to look at, if you cannot find a paper, just shoot me an email, I'll share that with you. I have a folder full of all those papers because I use them to make these slides, right? The reason why you should pay attention to this paper is because they are the only source of this information. You don't get it in any textbook, okay? All right, so, excuse me, I don't know what happened to my voice, but anyways, so let's see. This is total write access time to write access energy. We care about having lower energy and lower time, as you can imagine. So we love to have this corner, lower energy, lower time. Let's see who gives us that. This is our SRAM, the gold standard of speed. See, nobody even comes close. That's the reason why you still use SRAM, right? But in terms of energy, they're not really the best, but they're okay. They're not that bad either. And when I say energy, remember, this is only write access energy. That's not the problem with SRAM. The problem with SRAM is continuous energy. You have to keep them powered up, not just during write and read, right? So it's not really giving you the right picture. But there are propositions of making, this is a tangent. Wouldn't it be nice to have a non-volatile SRAM? Because that will solve the only problem with SRAM, that you have to keep them powered up. Well, not the only, one of the major. The other one is big area. How big? I'll show you in a second, but unreasonably big area. That's the other challenge. If somebody could solve that, that would be awesome. But at least non-volatile SRAM would be nice. But notice SOT, spin orbit torque based, 2T stands for two transistors, as you can imagine, right? They're kind of close competitor in terms of speed. I don't know if you could notice them here, but this is one and this is your SRAM. Well, that's what I mean by close competitor. Still orders of magnitude slower, but still, look at the other options. This is where STT lies. STT is even slower than SOT and more energy hungry. If you see, this is also logarithmic scale. So orders of magnitude more energy, at least 10x to 100x more energy for STT versus SOT. So you could save a lot of energy by going to spin orbit torque based approaches. Okay. Does that make sense? And I'm not covering all the other avenues of memories, as you can imagine. I just want to point out the ones that we covered, STT and SOT so far. Okay, and what does this mean? SOT with tungsten and tungsten telluride. So depending on what type of SOT material you use, the performance also changes, also varies. So you can only imagine people have tried to achieve the same structure with different kinds of heavy metal, and some work better than others. Okay, let's look at this area comparison and see how ORID you should be with SOT area being higher, slightly higher than 1T SRAM. Sorry, 1T STT MRAM. This is your SRAM area. Quite literally going to the roof, as you can see, right? If this is the roof, going above the roof. But everyone else, STT-MRAM, 1T, 2T, blah, 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 blah. I didn't cover the voltage control magnetic anisotropy MRAM, but it's okay. You don't necessarily need to worry about it at this point because these are the most prominent ones, STT and SOT. There are many other niche spintronic memories, which we will not have time to go over. But look at the difference. So your SOT MRAM doesn't look that bad when you compare that with an SRAM. So yes, you're not getting as small of an area as STT, but you are still okay to some degree. Do you care about only this much increase in area? Maybe, maybe not. That's why they want to portray the number. And look at the read access energy. In terms of energy, SOT MRAM, this is SOT, spin orbit torque, and this is STT. Clearly, significant reduction in read energy as well, not just write. Why is that? We didn't change the read mechanism, did we? The read, do you guys remember that the read is still through the MTJ? We didn't change the read mechanism. We changed the write mechanism. So you are getting significant benefit for write energy. This is literally, maybe an order of magnitude, maybe. Okay, but for read, it's not, maybe that much, but you're still getting some benefit because of having separate read-write path. Now you can optimize this other transistor to provide absolutely great read performance. And in doing so, you can minimize the energy. So anytime you have separate read-write path, think of it to be a blessing in terms of optimizing both read and write. So the metrics will definitely look better compared to a memory that has common read-write path any day. Okay, this is the last slide for this lecture, as you can see. Excuse me. This will open up, the discussion to the most advanced version of memory array to this date. It's called cross-point memory array. Okay, this was practically one of the topics of my PhD research as well. So imagine you have a magnetic tunnel junction, and instead of using a transistor, you can use a different nanoscale material as a switching element. Why do you need the transistor, folks? Can you imagine? Can you remind me why we needed a transistor in the first place? Let me show you. So you have a transistor and you have MTJs. Why did we need this transistor? To read or write? To be honest, that's not what we need the transistor for. I mean, if I could just take an MTJ and connect it to two wires, I could inject current through this wire and write it, or apply voltage across this wire and read it, and I would be just fine. Don't you think? But nobody asked me this question. See, that's how easily you are letting me go. See the point? Do you agree with me or not? Why did I even need the transistor to turn on the word line first and then bit line and whatnot? So all those secondary steps were not necessary. I could have just applied a voltage across it using the interconnects and whatnot. Yes, thank you. Remember, the memory is not about a cell. And oftentimes when you, this is a concept that's often missing in material science and physics. Oftentimes you'll see some fancy device and phenomena coming up and they're selling it as a memory, but they're just probing into one device. For example, a DNA, right? The preliminary works used to just take a DNA and write and read with probes. But that's not how you arrange an array. You're not going to manually program every cell in an array, right? You have to come up with a mechanism to automatically control the array and be able to select a specific cell to read and write. So what the transistor allows you to do is to make sure only the cell that is necessary to be accessed gets activated and others get deactivated. So the transistors are more, I mean, they're more important because they need to be off for the cells that are not used, not so much for the cell that needs to be accessed. If anything, transistors are detrimental to the cell that is being accessed. Remember cell tunneling magnetoresistance? It basically reduces the tunneling magnetoresistance by adding an extra resistance. So you don't like it for the cell that you are accessing, but you have to use it for the cell that you are not accessing. Let me show you one example of that, okay? So this is your MTJ, and let's consider that this, I mean, how can I, maybe I'll just cut through this. All these word lines are connected, and then all the bit lines will be connected. I'm going to show you quickly what happens to the cells that are not being accessed. Okay, and then this is another bit line. And source line is there as well. So imagine when you try to access one particular cell, like maybe this one, you activate the word line and you activate the corresponding bit line as well. Notice there is a challenge here. When you activate the word line, right? When you activate the word line, what happens to these cells, these transistors? They also get activated. Their gate also gets the full VDD. Don't you think? So these transistors also turn on. Oh, wow. One more thing. When you share the bit line this way and activate them, all of this bit line also get activated. So, I mean, again, when you're trying to access this cell, you're accidentally trying to access the others as well. So what do you do? What do you do? Any suggestions? Yeah, so there is one more option left for you. I don't know which color to use. Maybe, I mean, I'll go back to blue. All right, so imagine if I shared this other terminal this way. If one of them is horizontal, the other one should be vertical. That way, I could make, if this is VDD, I could make the other one VDD. That way, you have zero voltage across this cell. Even when the transistor is on, there is no voltage across it. So no current. You're safe. Only, okay, when you share it across this column, then you make it zero. That means this is VDD and this is zero. So you have the full voltage appearing across this. I know it's getting messy, but you only get it if you observe me draw. Are you lost? Should I repeat it? Okay. I assume that you're getting it, but if not, please think about it and let me know. I would be happy to go over it again. My point is, transistors allow you to turn on or turn off cells. Yes. So, I mean, again, not all the blue lines, not this one and this one. This is, I mean, I ran out of colors. So all the verticals are connected, all the horizontals are connected, okay? So sorry about this confusion. It's not connected here. All right. Yes. No. There comes the answer. Thank you. That's a great question. So it feels like you don't need the transistor. How about this cell? What happens to this cell? So, for example, if you apply, let's think about this cell first, the start one. Okay, so this is VDD. If this is VDD, then if you apply VDD here as well, just take notice. I know it's gonna be very confusing. VDD, VDD, so this is 0. But then, since this is 0, this is VDD, this will have a voltage across it. How do you save this cell? You turn off the word line. So you need a transistor. So to save some of the cells, you need the gate transistors. I know it's very confusing at this point, but trust me, it will get easier. My point is, if you have multiple cells without getting to the super detail here, horizontal and vertical, when you access a certain cell, the cell across the same row and the same column will share some bias voltages as the access cell. To save the rest of the cells in the same column or same row at least, you need to turn off the transistors or do something with the biasing. But you cannot live with just biasing or just transistors. You need to do both. You need to turn off the transistors as well as deal with the biasing to make sure they don't get disturbed. Okay, so that's why we need transistors. Actually, I mean, this is if you think about it, for such a small role, you are sacrificing so much area. That all the transistors are doing is like saving the cells that are not being accessed. Well, if we could achieve that with a very different approach without the transistor, that would be nice, don't you think? So there comes this cross point array. Let me explain what that is. In addition to, in place of a transistor, we use a device called a selector. That's a functional name, but the practical name is, it could be different kinds of material, including vanadium oxide, niobium oxide, silver, hafnia. And I'm not giving you a laundry list here, but the point is, all these materials have one thing in common. They are phase transition material, meaning they transition from one state to the other. And I will give you a more detailed view of this towards the end of this course, because I have a futuristic memory lecture where I will portray some techniques that uses this material as a selector. But I just wanted to quickly pitch this cross point array to let you know it's out there. And let me show you how it works. Okay, ready for it? It doesn't require bit line, source line, and word line. It just requires two line, bit line and source line, no word line. Why not? Because no transistor, no gate. You just have two terminals. So let me show you how it works. If you trust me, if you pay attention, it will make sense and it will be fun. Trust me. But you have to pay attention, because nowhere else will you get this detail. You have to probably go through like 20 different papers. So can I have you with me? All right. So we use, imagine every cell has a selector right under this MTJ. And remember, it doesn't need to be just with MTJ. MTJ is just a memory element. You could use other memory elements as well. The selector is just working with the memory element. Okay, so this small black square represents the selector. What the selector does, it transitions from being an insulator to a metal, and vice versa. So you could apply certain voltage to make it operate as a high resistance material like insulator, or make it behave like a metal. And if you look at the current voltage characteristics of this selector, it will look like this. Up to a certain voltage level, it will give you a really low current, and then it will jump and give you a really high current. Okay, orders of magnitude difference. And by the way, if you reduce the voltage, it will not get back to the insulating state at the same point. There is another threshold right here. You have to go beyond this threshold to make it get back to insulating state. Am I making sense, folks? But remember, it's not a memory. Why is that? Notice at 0, what happens? When you remove the voltage, it will always go back to insulating state. And next time it will start with this level again. Unlike a memory, unlike a non-volatile memory, okay? It cannot remember, hey, I was a metal before my power was shut off. It will always start as an insulator. So that's why it itself cannot be used as a memory, which I like. I don't need it to be a memory. I already have a memory, MTJ. I just need it to be a switch. Is it not a switch, if you think about it? Beyond a certain threshold, if you can somehow provide enough voltage to go over the switching level, then it could give you really low resistance. So I'm going to simplify this for the sake of our discussion and draw it this way. No. Excuse me. I wanted to use a different color. Maybe this one. Okay, I want to show that a switching occurs at a critical point. This is our critical voltage where switching occurs. If you pay attention, we'll be able to make sense of it quite easily. Let's see. So our bit lines will run horizontally. And source line or word line, whatever you want to call it, because you just have one more line, maybe source line, will run vertically. Okay, so when I try to apply access a cell, maybe let's choose a cell to access. Which one do you want to access? Diego, go ahead and pick one. Middle right, meaning just okay. Give me 1 second. Let me. Okay, this one. This one. Okay, sure. So this is the one that we're trying to access. All right. So what we do is we apply full VDD or excess voltage to the bit line, and we apply 0 to the source line. What does that mean? If you see let me quickly go to the other side. So one of these lines will have VDD and the other one will have 0. That means what is the voltage across the cell? Full VDD. Do you see that? Okay, all right. So you have full VDD appearing across this cell. But the problem is when that happens, how about these other cells? They have VDD in one side. So what should I do to the other side? Remember, let me assume that our VC, let's take some number. Imagine this is our VDD. Still with me? Let's assume that this is our VDD. So VC is close to VDD, or we choose the VDD to be close to VC, but VDD is above VC. So when you apply VDD, that means the selector will behave like a metal. It's as if it's not there. It's just giving you full access to the MTJ. Okay, but this is where VDD over 2 is. So VDD over 2 is less than VC. So VC is between VDD over 2 and VDD. Okay, how can you tune the VC? By tuning the geometry of the material. You can make it bigger or smaller, wider or narrower. By doing so, you can change the critical voltage. You can also change the material entirely. Different material has different critical levels. But at the very least, you could do that. Still with me? Okay, so VDD is above VC. VDD over 2 is below VC. So now let's see. You apply VDD here. But what happens to these other cells? They get VDD in one side. Okay? If I apply, I'm going to tell you something wrong first. If you apply 0, you have full VDD. So it's not going to work. If you apply full VDD, then you can have 0. We are talking about these two cells, right? You see that? If I apply VDD to these source lines, you have 0 voltage appearing across them. But then there is a problem. What's the problem? The other ones. What do you do? So I'm going to give you the solution first, and then we'll analyze it together, okay? To save time. So what we do is we apply VDD over 2 in all the other rows and columns. So only the cell that is being accessed, for that corresponding row and column, you apply 0 and VDD. For the other ones, you have VDD over 2, VDD over 2, and here, VDD over 2, VDD over 2. Let's now analyze together and see what happens to them. Still with me, folks? Okay. So what is the voltage across this cell? VDD minus VDD over 2. So the effective voltage is VDD over 2. Do you guys agree? What is the selector doing here? Is it insulator or metal? Why? Because VDD over 2 is less than VC. Okay. So this is insulator. This is also insulator. Okay. How about this cell, folks? So bit line has VDD over 2, source line has VDD over 2. This is perfectly 0. So for sure, this is insulator. This is also insulator. And I mean, I can keep going. This will also be insulator. This will also be insulator. This will also be insulator. Only the cell that is being accessed will be metal. So basically, it's like a transistor turned on and the others stayed off. It's easier said than done. It's not as easy as it sounds, because I haven't showed you what happens to the other one. And then there is a chance of having oscillation and whatnot. It's a complicated design space, but the idea is simple, is it not? Idea is simple if you could achieve it through proper design. So to achieve this memory, cross-point memory, Intel and Micron, they joined force, two of the biggest semiconductor entities in the US. They literally joined force. I mean, as you can see, they are competitors, but they had to join force, work for 5, 6, 7 years together to realize this. By the way, they funded a portion of my PhD as well, for example. Okay, as you can see. So this is how critical this was, because it solved the scalability issue. And we now have 3D crosspoint, by the way. It's there. Okay. I forgot the commercial name. I think it will come back to me. But the Opten, Intel Opten or something. Okay. But I can double check and get back to you on that. But they have a commercial product as well, based on this 3D crosspoint and whatnot. But at some point, Samsung also looked at it for a while. They used vanadium oxide. They published some papers as well on that. But I don't think they pursued it any further, especially because their competitors were so serious about it. It's difficult for them to compete. Okay, anyways, setting those commercial stuff aside, I hope you understand the technical aspect of it. Do you see the merit? Okay, it's not yet there because of some other additional secondary issues that it brings in, which I'm not getting into in this lecture, but maybe towards the end of this course, once you have a lot of knowledge about all the other memories, we'll revisit this and talk about more opportunities there. Okay, so I'll take a couple of minutes to clarify a few things. I've got final confirmation from Intel Labs, and the date is in end of March, and final confirmation from IBM Research, thankfully. As you can see, it is a lot of effort. So I'm gonna I'm still waiting to get the abstract and bio from the Solidigm folks, and hopefully they'll send it to me soon. Once I have it, I'll send out an announcement to all of them. I'm still pushing for Micron. I don't know whether or not that will happen. That's why I'm still holding on to, as you can, I mean, I'm sure you have the question, why flash memory is not being dropped here. I really hope that we get someone from Micron. If not, it's okay. I can do it any day, but it's not a big deal. I'm sure you'll like this, industry talks. Just wait for them. Maybe let's go through one of them. I'm personally excited, especially the last cycle I invited there is at least one common person who also gave a talk in the last offering of this course from Intel Labs, the same person. It was great. And this is linking memory with AI. So basically, how do you co-design memory specifically for AI applications? Hopefully you'll learn a lot. Okay, so just giving you some sort of clarity as to why I'm pushing one lecture versus the other. Okay, but it's okay. I have everything ready, so I can just get to the next lecture without any other concerns. Did I preempt your question? I was expecting, okay, where is Flash? Anyways, okay, so ferroelectric memories. This is, as you can imagine, another type of emerging memory. We'll just barely touch upon the surface today, and then we'll catch up in the next class. This is another memory that is very close to my heart. I had a lot of work on this, especially within the last 5 years or so. So ferroelectric material, before we talk about the memory, let's talk about ferroelectric material. Okay, what is that? A ferroelectric material is very interesting because it provides you with a hysteretic electrical characteristics. And here is what I mean by that. This is polarization. think of it like a charge instead of polarization. Polarization is nothing but charge per unit area. So if you divide the amount of charge stored in a material with its surface area, you get polarization. So sounds fancy, but it is just basically charge, nothing else. Okay. And in the x-axis, you have the voltage applied across it. So if you take a material, apply some voltage across it, by applying significantly high positive voltage, you can create a positive charge density in the material. By applying a negative voltage with opposite polarity, you can create a negative charge density in the material. Okay. What's interesting is that it's not just you can create the charge. So if you apply a high voltage, sure, you go through this cycle. But then when you remove the voltage, get to zero, this is what happens. Notice at zero, what do you have here? Still some polarization or charge. So once you charge up the material, when you remove the voltage, it still remembers what it was storing. When will you be able to get rid of the charge? To get rid of it, you have to apply a voltage in the opposite direction. You see that? It's exactly like the ferromagnetic hysteresis. How many of you have seen hysteretic curve in high school, right? But remember, it looks extremely similar, but it's not ferromagnetic. It's not magnetic field. There you had magnetization. BH curve. Remember BH curve? Okay, so it's not magnetization. It's basically charge, but it looks exactly the same. That's why the name, instead of ferromagnetic, it's ferroelectric. You're dealing with electronic properties, not magnetic property. Okay, so it's not magnetic domain, but it holds on to a charge. To get rid of that charge, you have to apply voltage in the other direction, other polarity, and then you can get to zero charge. Or if you keep applying that polarity, you can get to a point where it will basically switch to a negative polarization. And then once you remove that voltage, get back to zero, it will get stuck here. So you can either create a positive polarization or a negative polarization. I don't have to tell you anymore. Like, okay, there you go. We have a memory. By using positive polarization as 1 or negative as 0, you can have a memory. And interestingly, this is non-volatile. How do you know that? Anytime at 0, there is a stable state, that's a non-volatile memory. The moment you get back to 0 volt, that represents power loss. Basically, you have lost power, but still, you can either get stuck here or here. So go with me on this journey as I draw. Trust me, after I draw, it looks really, really messy. But imagine, basically, this is how the material works for the first time, very first time. You start with 0 charge at 0 voltage, literally no charge. Okay, it's called pristine condition. Okay, so at pristine condition, once you start applying voltage in one direction, it gradually goes up and starts accumulating charge like this. And then if you let go, it's like pulling a rubber band and letting it go. So if you let it go, it will get stuck here. Making sense? It will lose some of the charge, but it will hold on to some. This amount of charge that it is holding on to is called remnant charge or remnant polarization. Whatever is remnant, that's all. It remains even when you remove the voltage. Okay. Okay. So now, okay, what happens if I restart and apply the same polarity? What happens then, folks? Let's see. Basically, you restart. Material remembers, hey, I already have this much charge. So it will basically traverse through this trajectory, back and forth, back and forth. It will not go back to the other one, as you see. So it remembers. Like if you've seen Game of Thrones, the North remembers. Similarly, the ferroelectric remembers, basically. Okay. So how can you get rid of this charge? How can you make it forget? How can you erase this charge? You have to apply a voltage in the other polarity. And maybe you're just happy with completely erasing it out. But if you apply high enough negative voltage, it will get to the other polarization. Making sense, folks? And then if you remove the voltage, it will get stuck here. Okay, next time, when you start again, it will remember, hey, I had a negative polarization, so I should follow this trajectory. All with me so far? Okay, so that's how so to switch from one type of memory to the other, you need two different polarity of voltages, positive and negative. That's one take-home message. You already see what you need to do. how can you sense? The more important question is, okay, I understand that you have different charges, we could represent them with 1 and 0, but how do you read charge? How do you know what type of charge is being stored? We have to find out a way to electrically read or electrically sense what is being stored, which is not as straightforward, which I will discuss soon. And that's where the major challenge lies in ferroelectric memory. But don't worry, engineers will not just let it go like that, because I want to show you this figure before closing today's class. Sorry. Oh, by the way, this is an example of a ferroelectric PV curve. This is another example of a ferroelectric PV curve. Just wanted to close off this slide. You see, there is a spectrum. It could be narrower, it could be wider, it could have higher remnant polarization, it could have higher coercive voltage, which I didn't explain. By the way, this voltage that you have to exceed to get to the positive polarization or negative polarization is called the coercive voltage. You can represent this with VC. When you divide voltage with thickness of the material, you get electric field. So oftentimes we use electric field, coercive electric field instead of coercive voltage. These two are fundamental material parameters that we need. Okay, remnant polarization and coercive field. Are you still with me? Okay, give me 5 seconds, please. Just wanted to quickly show you. 1920 is when people started looking at ferroelectric material. We have recently celebrated 100 years of ferroelectricity, recently, in 2020, by the way, okay? So people have been looking at it for a while, but only after about 50 years or 30 years, people thought about using it as a memory. Because before that, they didn't need to store anything, okay? But then, decades after, in recent years, 1990s to 2020, there are more activities, as you see. So people figured out ways to solve the biggest problem that the first generation ferroelectric memory had. So I will explain the first generation first in the next class, and then we'll see the more advanced versions. Okay. Okay. Thank you. Sorry, I went over like a couple of minutes.